All right, so we're looking at section 4.4, modeling and optimization today. So we're going to take some of these ideas we've been talking about. We're not so concerned with the whole concavity, point of inflection type stuff with this. This is all just first derivative work for the most part. But this is probably the most used application of calculus out there, is trying to optimize stuff. Well, what does it mean to optimize something?
Look at it in perspective.
Nope. Nice guess, though. But that's not it. Anybody else? What's optimization?
Make the best out of something.
Right, get the most out of something, right? Basically, it's not what you said at all. So to get the most out of something, so another way of looking at it is to get the maximum of something out of whatever it is that you have. So we know how to find maximums, or in some cases it might be minimum, depending on the situation. But we know how to find maxes and mins, though. We've been talking about this quite a bit so far in this chapter. So we're going to take that idea, okay, those techniques we talked about doing derivatives and setting them equal to 0, yada, yada, and we're going to apply that to some real-world type stuff and do some optimization with those techniques. Okay? So there is a basic 6-step strategy for these that we're going to jot down here that you can follow. And some of these are things that you would do anyway, but I think it's important just to kind of have this in your notes as a little bit of a roadmap for you if it's helpful. Number one, and this might, like I said, be kind of a no-brainer, but understand the problem. So know exactly what it is that you're searching for and what it is that you have to work with. If you're given some kind of an equation, okay, what are the variables in the equation? What do the variables in the equation represent? What is it exactly that I'm trying to maximize or, in some cases, minimize? So understand what you're looking for with that. Number two, and sometimes this can be the most difficult step, develop a mathematical model. Now, some of these, you're going to be given an equation, and so step 2 is kind of a moot point. But there are other ones where you have to actually come up with the equation based on what the situation is. And that can be challenging. Most of the time, the problems you're going to be looking at where you have to do this are going to involve some kind of geometry. And we're going to come back to some of our geometry formulas again today, involving volume and area and that sort of thing to help us with that. Okay, so that's kind of a big step in the process here. Number 3, and this you might not always be able to do depending, but if you can, if it's a calculator friendly problem, you could graph the function. So I'm going to put a little asterisk over here. Okay, so that's kind of a sometimes step. All right, but if you have a graphing calculator available for the problem and you have your model, it's a good idea to graph the model and see what you have. Okay, remember we're looking for maxes and mins. That can be pretty helpful. Number 4, identify any critical points or endpoints. And I'm going to just put in parentheses here, domain. Okay, the critical points, okay, that we're going to want to know those. Where are the maxes and mins exactly? That's what that's referring to as far as critical points. And then the endpoints, actually this should not say or, this should say and. You should want to do both. I put domain on there because depending on the situation, even if the model you come up with, let's say, is some kind of polynomial, and we know that the domain for all polynomials is negative infinity to infinity, But maybe for the situation you're working with, negative numbers for x doesn't make any sense in the context of the problem. And so in that case, then your domain might be 0 to infinity or something like that, which creates an endpoint, right? So if you have some kind of restriction on what you're allowed to use for your variable, then you're going to want to restrict what your domain is, and that could create some endpoints that could be maxes or mins then as well, right? We've looked at that before. When we're looking for critical points, we're looking for maxes and mins. Could be something in the interior of the interval, or it could be something out on the edge on one of the endpoints. So we got to consider that stuff too. Number 5, solve the mathematical model. And in most cases, this is going to involve taking a derivative and setting it equal to 0. Because remember, if we're trying to maximize or minimize something, we found before that those occur when the first derivative is equal to 0, or at least that's potential. So we're going to go about that process quite a bit. And then number 6, interpret the solution. So once you have, okay, the max occurs at x equals 3. What the heck does that mean in the context of the problem then? Okay, so kind of bring it back then to where you started from. Okay, so what is this answer really telling me? That's going to be your last step. So interpret. Can I spell interpret? I think so. Interpret. Yeah. The solution. All right, and that's your basic 6-step process. We're not always going to do all 6 steps, but in general, that's kind of how we're going to flow through these. Okay. So, going to start off with one that is not so tricky as far as building the model and that sort of thing. But it might seem kind of difficult getting started because you're not used to doing this kind of stuff, okay? So I'm calling it easy, but I don't want you guys to be like, oh, geez, I couldn't do that. Just give it some time. It's fine. So anyway, so our first example is find two numbers. Whose sum is 20 and whose product is as large as possible. Okay, so understand the problem. Is it clear what we're trying to do here? What's your answer going to look like? What are you trying to find? 2 numbers. So I'm going to have 2 numbers when I'm done. Okay? And what am I trying to maximize about those 2 numbers? Their product. Okay, so somehow I have to get the product of these 2 numbers as large as possible. But I got this constraint on these 2 numbers, though, right? What has to be true about the 2 numbers at the same time? They have to add to 20. Okay? So I want to find 2 numbers that when I multiply them together, it's as big as possible, but they have to add to 20. Okay? So develop a mathematical model. This one might be tempting to just start trying numbers. Okay? Based on the way this one's written, you might just say, okay, well, let's go with 12 and 8, multiply those together, or maybe 10 and 10, I'll multiply those together, and just keep trying different combinations until you come up with whatever you feel like is the biggest. Okay? That's a way to go. Now, there's no 100% certainty that you're going to have the right answer because there's always other numbers you could try. It doesn't have to be just integers, by the way. It could be decimals or something. So you could get a sense of where it's going to be, but might not know for sure that it's the biggest. If we actually develop a model, though, we can do it. So anybody have any ideas of how we might get this one kick-started? I'll give you a hint. Start with the constraint. Can you build a model that just shows the constraint? Okay. All right. And then we want want to show that the product is as large as possible. So I'm going to go with, call P product. The product has to be A times B. And this is what I want to maximize. So I want to maximize P, which if I go to the, because I'm not going to be able to graph or identify endpoints, critical points, blah, blah, blah. If I go to solve the mathematical model now, I have to jump down to that one. If I'm going to maximize that, I have to take a derivative of that. But what's the problem with taking the derivative of that? Yeah, usually it's just y equals something involving x. There's only two variables involved. I got 3. Anybody see a way that we can avoid having to use 3 variables and knock it down to 2? Somebody just said it. I heard it.
Bailey said it.
Bailey, what'd you say?
Substitution.
Substitution, thank you. That constraint is there for a reason, right? If we can take that and substitute it in the other one, then we can have a model that only has 2 variables in it, and we can actually do a derivative and do something with it. Okay? So, what do you guys, or how do you want to go about doing that then? Okay, yep, it doesn't really matter. So, A equals, let's say, 20 minus B, and then make a substitution into P. So, P is equal to 20 minus B times B, or it's going to be easier to work with if you just distribute that. 20b minus b squared. And now we're ready to do the derivative and maximize what we have. So, derivative of that, p prime would be 20 minus 2b. And if I'm going to maximize, what do I want to do with my derivative? Where would maximums occur? What would be the value of the derivative? It has to be 0, right? So 0 equals 20 minus 2b to try and maximize this thing. And I bet you can probably do that in your head, but what's the value of b? 10. Okay. Remember, our answer is supposed to be 2 numbers. A and B, right? If B is 10, though, what does A have to be? 10. Also 10, right? So our answer then would be A equals 10 and B equals 10. So apparently if you choose 10 and 10, that product is going to be the largest. And the question might ask you, what is the maximum product? So what's the maximum product? 100. Okay, if you multiply those together, you get 100. There are no 2 numbers that you can choose that add up to 20 that will give you a product bigger than 100. You can try it. 20 and 1 gives you 20. 18 and 2 gives you 36. And it just, yeah, doesn't work until you have them both be 10. All right, anyway, so that's kind of the general strategy. Okay, again, interpreting our solution and all that at the end. Let's try another one. And this is going to be more of a, well, kind of sort of geometry. All right, that's kind of a crappy sine wave, but that's supposed to be sine. And this is a rectangle. What? Shut up. All right, there's my rectangle. All right, good job. So I want to know, what is the largest area for that rectangle that I could get? And it has to be trapped under the sine. Oh, yep. Mm-hmm. So what is the largest area this rectangle can have if it has to be what we call inscribed underneath the sign? So what that means is the corners have to touch. Okay, so these top two corners of the rectangle have to touch the graph of sine. Okay, so let's start with, what are we trying to maximize here? Area. Okay, and it's a rectangle, right? You guys can all find the area of a rectangle. How do you find the area of a rectangle? Length times width. Okay, so let's say this is our length, this is our width. As you guys are going to be a little more familiar with here in a minute, you're going to have to create your own variables a lot of the time. These first two questions, we've been doing that. So length times width. So the area equals length times width, and this is what we want to maximize. Okay, but again, we got the same problem, right? We've got too many variables to work with there. So somehow we need to do a substitution. The constraint on this one is not some equation we've come up with. The constraint is the graph of sine. We want to maximize that area, but it's got to fit within the confines of sine. Okay? So here's what we have to do. We have to take W and L, and we have to somehow write those in terms of the function that we're working with, sine. So let's start with this, the width. Okay, this right here. Do you see how that is basically just the y value of this point right here? Does that make sense? Okay, so if this is the same as the y value of the function at that point, remember this function is y equals sine x. So W then is equal to simply sine x, because it's the y, and y equals sine x. Okay? We okay there? No? Not okay? Okay. It's because this length right here is the height the point is off of the x-axis, right? And the height is always y. And y is equal to sine x. So it's got to be the same. Oh, okay. All right. Now L is not exactly x. It would be nice if it was, but it's not. Okay? Because if we're over a certain distance, like right here, let's say this is, our x over, L is not like the distance from the origin over a certain distance. There's this gap here, okay? And this gap is x. And this gap over here is also x. Okay? Because it's all symmetric. Does that make sense? However big this is, this over here would be the same distance because the symmetry of sine. Okay? All right, so this entire thing up to here, those of you that remember your sine graphs well, where is that point? Nope. Pi. So, yeah, because it's half the period, right? Can you give me L in terms of x then? Exactly. Did you guys catch that? L is pi, that whole distance, minus 2x. Take away the two little gaps, right? Okay. So now we have an equation, if we do substitutions with both of these. Let's put parentheses on both. All right. I now have a function completely in terms of x, which means I can do a derivative. I can set it equal to 0. I can maximize the area. Okay? So A prime I got to do a product rule to do that. Okay? So it would be, see, derivative of sine is cosine times pi minus 2x. And then plus sine x times the derivative of this would be negative 2. And that I want to set equal to 0 and see what are my solutions and all of that. Now this one, I don't believe we're going to be able to do by hand. We're going to have to do our calculators for this one. Because setting this equal to 0 and solving, you don't have a method you can do that by hand at this point, right? So we're going to look for some solutions on the calculator to do that. So what I'd like you to do is, I'm going to just simplify this up so it's going to be easier to type into your calculator, but negative 2 sine x plus pi minus 2x cosine x. I'd like you to type that into your calculator. Make sure you're in radians when you graph this thing. And what are we looking for with this graph? Nope. 0. We want to know where is this equal to 0. Okay? So, graph it. Check it out. See if we can find it. I suppose you could just as easily graph this first one and look for maximums too, right? As long as you're able to graph it on the calculator, why not, right? But let's do the derivative just because that's what we do in calculus. But technically, nothing that says you couldn't do it the other way. You're going to want to make your window pretty small. I think with x, if you only make it up to pi, that should be fine. It's 0 to pi.
She doesn't know Mr. Jacob.
Wow.
Sorry.
Sorry. Okay.
You don't know him? Yes, you do. Yeah, but you still know him.
Okay. Shh. Now, I only made my x go 0 to pi. Take a look at the picture here. Does that make sense why I did that? Yeah, we're trying to figure out how big x could be. And yeah, x is going to be pretty tiny, right? It's definitely not going to be any bigger than pi. So the solutions that I'm getting here, when I'm looking for my zeros, quickly do this here. So I got 0.7104. And then there's a second one in there. Quickly find that one. All right. So the two solutions I found were 0.7104 and 2.431. One of those is going to be a maximum. One of those is going to be a minimum. Take a look at the graph. This is the derivative, remember. And explain to me how I know that the first one is actually a maximum and the other one is a minimum.
Because if the slope is like going down in that one, so that means like the slope is getting less and less steep
Mm-hmm.
on the other one. It's like it starts off by going up because it's above the 0. So you know it starts by going up and then ends up going
Right. Think positive and negative, because this is measuring slope, right? So if it's above the x-axis, it's positive slope. If it's below the x-axis, it's negative slope. A maximum happens when you have a positive slope that changes to a negative slope, right? So it has to be this one. Positive slope changing to a negative slope, right there. Okay? So x, we haven't actually answered the question yet. That makes this happen is this 0.70 or 0.7104. Now, the question asked, what is the largest area? So what am I going to do with that answer then? Okay, do sine of 0.7104 and?
And do pi minus 2.71.
We have to plug this in for the width and the length and multiply them together, right? The actual area is width times length. So plug them in and multiply. Or just simply plug into this equation down here that we made for the area, right? Plug in our value of x, see what it is, right? So let's do that. So our area is going to be the sine of 0.7104 times pi minus 2 times 0.7104. And is it about 1.12? Should be. I didn't type it all in myself, but I cheated and looked at the answer. So, are we good? Good. Okay. So, that's the largest that rectangle could get. 1.12 square units if it's caught under the sine. Okay. So, some other stuff. I talk about my friend, the packaging engineer, in here a little bit. He designs boxes to get the most out of them and stuff. Yeah. We're going to do a little something kind of here. Okay, so here is a piece of cardboard, also a rectangle. So we're going to start with like a stock piece of cardboard. We're going to cut little corners off of this thing to turn it into a box. So let's say that this piece that we're working with is 10 inches this direction and 30 inches in this direction. And we're going to cut off a corner here and here. And then we're also going to cut here and here. So all the stuff that I'm shading in is going to be like excess that we're going to cut off. Alright, and then these dotted lines just I'm going to put on for emphasis here, but these are places where you would fold the box. You know, I haven't talked to him in a few years. I'm not sure if he does this exactly. But I do know he's a packaging engineer, and I do know he designs boxes to get the most volume out of the least amount of material. So, which is what we're going to do here. We have this piece of cardboard that's going to make this box, and I want to know what's the largest volume box we can make by cutting little corners off of it like that. Okay? And so, just so we have a variable here of some sort, we need to know how big a cuts do we need to make here off of these things to make this the largest volume box possible. So, and these would be little squares, so they're x by x, and they're all going to be the same size. All right, and then the rest of this cut is just determined by how wide this is, because to wrap this thing around, this length here would have to be the same thing as this length here. Okay? We'll talk about that a little bit more as we try to make our equation here, but that's kind of the gist of how this thing looks. So, some people are better than others. I recognize this fact. It's kind of it's a hard skill to develop if it's not just in your brain already. But some people can take something like this and I say, okay, you're going to fold that into a box, and they're like, yep, see it. Got it. Other people are like, what the heck are you talking about? That's not a box. It's just flat, and I don't understand how that's supposed to work. So I'm going to try and kind of help you here. So if you think about this thing laying flat, kind of take this two-dimensional thing and then take it out in your brain in 3 dimensions, and let's say you're going to drop it on a desk, okay? You've got these 3, okay, pieces. You got 2 that are going to fold up like this, 1 that's going to fold up like that, and then you've got the wraparound part that's going to come up and wrap around like that. Does that make sense? 2 sides come up, 1 side comes up, other side wraps around it, makes a box. Okay? So it's a solid top on it and everything, box. So what we need to figure out is, what are the dimensions of this box? If we're going to maximize its volume, we need to figure out what's the length, width, and height of this box. So I'm going to come over here next to it, and I'm going to sketch what this box might look like all put together. Okay, so something kind of like that. And we're going to see if we can take what's here and transfer it over to there. So first of all, the height of this box would be what? Think about all those little flaps you're folding up. What's the height of the box? X. Good. It has a height of X. All right. Now the width of the box, which would be this dimension right here. Look at this picture over here again. How can I figure out the width of the box from my picture? Be what? Other side. That's the length. 10 minus 2x. Yeah. Now the length is difficult because the length is this right here. But you have 2 of the lengths, right, in this picture? Okay. So the whole thing's 30. You got a couple of x's to get off of there. So you can't just do 30 minus 2x because there's 2 left over after you do 30 minus 2x. But they're both the same size. Divide it by 2, right? 30 minus 2x would give you how this and this together are, and then just divide that by 2, and that gives you the length of one of them. Does that make sense? Okay. So over here then, this length of the box is going to be 30 minus 2x divided by 2. Well, okay, but that would actually be what then? 15 minus x. So use that, yeah. And so now it's pretty easy to come up with a volume equation, right? Length times width times height. Take those 3 dimensions we just came up with and multiply them. So length times width times height. There's your volume. Now, if I'm going to maximize the volume, I got to take its derivative, set it equal to 0, do all that again. If I'm going to do a derivative of this thing, I don't know about you, but I'm going to multiply it. I want to multiply that all together, get a nice polynomial, and then use that to do the derivative instead of having to try to do a product rule a couple of times here. So, let's see, we got 150 minus 10x minus 30x plus 2x squared all times x, which is 150x minus 40x squared plus 2x cubed. Okay? So we're going to roll with that one, I think. So its derivative, v prime, is 150 minus 80x plus 6x squared, which is a quadratic, which we can handle. Going to set that equal to 0. All right, now if that's all equal to 0, before I start jumping into the quadratic formula or something like that, take a look at your three terms there. Can't we take out a GCF before we begin here? What's something that goes into 150, 80, and 6? 3 does not go into 80. 6 does not go into 80. 2, thank you. All right, so let's use that one. We'll go quadratic formula on this thing. So x is equal to negative b, which would be 40, plus or minus the square root of negative 40 squared, which is the same as just 40 squared, minus 4. A is 3, b is 75, all divided by 2a, which would be 6. All right, so let's work that one through just a little bit here. So 40 squared, 40 squared minus 4 times 3 times 75, that's 700. So 40 plus or minus the square root of 700 divided by 6. So we'll do it once with the plus here. So 40 plus square root of 700 divided by 6. So we got 11.076. And then if we use the minus, 40 minus the square root of 700, and then divide that by 6, we also get 2.257. So again, we're in a situation where we've got two separate numbers that could represent what we need for x to maximize the volume. How do I figure out which one actually maximizes the volume, though? Plug them in and find out, right? Put them in the volume formula and see which one gives you a bigger number. There's your maximum. And guess what? The other one's going to be the minimum, right? Okay, so let's see what we get with each of these. So V of 11.076, 150 times 11.076, minus 40 times 11.076 squared. I hope somebody's typing this in right now so I don't have to do it. 0.076. No, you plug into V. Definitely the volume. Because V prime, what's it going to get you? If you plug those numbers into V prime, it'll get you the slope, which is 0, right? We kind of already did that. So, yeah, definitely the original. All right, so did anybody plug that in for me? All right, we got a few people doing it so we can verify answers here. That's good. Negative 528. Negative 528. So I'm thinking that's not the right answer. What do you guys think? Yeah, nah, probably not. Okay. Try the 2.257 once. Let's see what that one gives us. That sounds more reasonable. So, David, what was it?
281.03.
Anybody else get that same thing? Nobody else was bothering to try it? All right. Now, let's take a look for a second at the original problem here. 11 didn't work, but 2 did. Look at the geometry of the picture at the beginning. We talked about the whole domain idea, how you might have to have some restrictions. Look at the box. What is the biggest that x could possibly be? And still make a box. Not 10. Less than 10. A little 5. Look at the side here. I'm chopping an x off here and an x off here. If those are any bigger than 5, I'm bigger than 10 and I don't even have the whole, I have more than the whole side. Right? There's no way you can make x bigger than 5. So the domain, and if it's exactly 5, there's no, so it can't even be exactly 5. It can't be any less than what? 0, right? Because it's got to actually exist. You can't have a negative side length. So that's the domain. So for our answers to make sense, the number that we're using to create these corners has to be some number between 0 and 5. No other way to do it. Okay? Well, look at the 2 answers. Look at the one that worked and the one that didn't. The one that didn't is 11.076. Well, duh, that's not going to work. That's not even physically possible. The one that did work, 2.257. Oh, that's nice, right between 0 and 5. We know it's the right one. Okay?
That's not the right answer.
It's not the right answer, though.
It's 157.78.
David!
Wow.
Wait a minute, check.
I did it twice. And got the same answer both times.
That's pretty legit. Okay, 157 point what?
78.
0.78. Now, so what should be my units on this? It's 157.78 what? Inches cubed, because this is actually the volume, right? So if I that piece of 10-inch by 30-inch cardboard, the largest box I could make would have a volume of 157.78 cubic inches, and I'd have to cut squares that are 2.257 inches on either side to do it. Okay. Yeah, go do that on your own. Going to bring in a couple type of now. We're going to do a little econ, and we're going to do a little physics, and we're going to be done. Who here knows what marginal profit is? Yes? Macro, micro, you should have talked about that a little bit, right? Or does he have that thing in his room that says, like, if MC is greater than or equal to, or MR is greater than or equal to MC, do it? Right. Or in this case, we're going to talk marginal revenue. So there's this idea that if marginal revenue is greater than marginal cost, then you should do it. Is kind of the big econ thing that Wiersma likes to talk about. Well, I'm going to explain to you in terms of calculus why that's the case. Does he? Well, now you can act like you know what he's talking about. So profit, for those that are not in econ, I want to make sure this is understandable for you guys. Profit is defined as revenue minus cost. Does that concept make sense?
Yes.
Revenue is the money that you make when you sell your item. The cost is how much it costs you to make it. So your profit is the difference between the two. How much are you coming out ahead? Okay, hopefully your costs aren't more than your revenue, because then you're losing money. But an equation for profit, an equation for revenue, an equation for cost, it would look something like this. P of x equals R of x minus C of x. Okay? And x would be number of units produced. Or sold, actually. It has to be number of units sold. Otherwise, you don't have any revenue. Okay, so it could be some formula, and I don't know, and it depends on what it is that you're producing, and those things could be different. But whatever your revenue equation is minus your cost equation, that's going to be the equation that you would use to calculate your profit. Okay? Now, in econ, when they talk about marginal revenue and cost, a marginal is the rate of change of your production. Okay? Or the rate of change in the amount of money that you get or amount of money it's costing you, which is essentially just a derivative of revenue or cost. There's also a marginal. So if this is the case, the marginal, the derivative of, using our derivative rules, should be the derivative of revenue, marginal revenue, minus the derivative of cost, marginal cost. Okay? Now, what do we want to be true about profit? We want to do what to profit if we own a business? We want to maximize the profit. What should be true about P prime then? We want P prime to be what? 0. Okay? If we're going to maximize profit, that's got to be P prime 0. So 0 equals R prime minus C prime. If that's the case, then that's going to be true, right? We want the marginal revenue to equal the marginal cost. If that's true, then we're going to maximize our profit. Or, we got to be careful though, or could be, if the derivative is 0 for profit, we're minimizing profit too. We got to double check that it's actually going to maximize it instead. Okay? But this is key, all right, to this idea is your marginals for revenue and costs have to be equal to each other, and that's going to be a potential to maximize your profit, and then we just got to double check the numbers and see if it works. So let's do an example. Let's say our revenue is 9x, and our cost is x cubed minus 6x squared plus 15x. Now, I don't know where businesses necessarily come up with these equations for revenue and cost. The revenue, actually, I do. The cost, I don't. These are crazy. I don't know. But the revenue, think about this for a second. If x represents the number of units sold, and my revenue equation is 9x, how much each unit cost? $9. Yeah, how much are we selling it for? $9, right? So that makes a bit of sense. This right here, I don't know. It costs us something cubed minus 6 something squared plus 15 times something. I don't know where they would get that. But it's not important. If we know what the equation is, we can at least use it and figure out where this maximization needs to happen. Okay? So if this is the key, right, we want to maximize profit using these equations, then let's set those derivatives equal to each other and see what we get. Okay? So we want to maximize profit. That's what we're going for here. Okay, so x is 9. C prime of x is 3x squared minus 12x plus 15. And so those two equal to one another. So we get that when you set them equal to each other. And then if we're going to actually solve this equation, let's move this 9 over to the other side. So 0 equals 3x squared minus 12x plus 6. And let's see, we can pull a 3 out of that thing as well, right? So 0 equals x squared minus 4x plus 2. And I don't think you're going to be able to factor that necessarily. Two numbers that add to negative 4 but multiply to 2? No, can't do that. All right, so quadratic formula. So I'd like you to do this on your own because you've done it enough. Use the quadratic formula. There's going to be 2 answers, okay? Just do that step real quick right now. Give me your 2 answers. And then we'll analyze those and see what we got. All right, what do we get?
3.41 and 0.586.
So about 0.59 then? Or going 2 decimal places apparently.
I did like 3 sig figs.
Oh, I see. I'm not. Okay. So 3.41 and 0.59 are going to be those 2 potential places where we might maximize profit. So how do I know which one actually? Because one of these maximizes the profit, one of these minimizes the profit, or another way of looking at it, maximizes the loss. So how do I know which production level I want? How many should I produce? Plug them into what? Plug into here. Yeah. Because if you want to do it this way, why not just come up with the profit equation and plug it into that? Because that's essentially what we're looking at, right? And revenue minus cost. So our profit equation is 9x minus x cubed minus 6x squared plus 15x. Please don't forget the parentheses. Could do it that way. Okay? Take each one of those 2 numbers, test it out. Which one actually maximizes the profit here? So I'll give you a hint. One of them comes out to a positive number. One of them comes out to a negative number. The one that comes out to a positive number is the one you want. So which one comes out positive? 3.41 should give you a positive. 0.59 should give you a negative. So this is the production level you want. Now, in the context of the problem, if X was just strictly number of units sold, we would have to produce 3.41 units, or maybe just 3 then, which seems kind of silly. I'm going to make 3 of whatever this thing is that I'm making, and that's it. Well, usually these equations, just so you're aware, and this one probably would have been this way as well, usually X is not strictly number of units sold, but maybe like number of thousands of units sold, something like that. Okay? So if X in this case was talking about how many thousands of units sold, okay, then how many should I actually be producing? 3.41 thousands, which is 3,410. So I should be making 3,410 said items to maximize my profit. Okay? So if you were working for a company and you were trying to figure out, what's going to be the best situation, how many should we put in an order for to make, you'd be doing this kind of calculation to figure that out. Okay? So that 3,410, that's going to give us the biggest bang for our buck, so let's do it. Let's make that many of them and go for it. So, last example, and then I'm done. We're getting kind of down to the end here. Whoops. Yep, I should have time to do my last example here. We're going to do a little bit of physics. We're going to talk about a pendulum, and then be done. People that are in physics, people that are good with physics and perpetual motion and that sort of thing, what kind of equation do you suppose I'm going to use for a pendulum, for its position? Any idea? Give you a hint. It keeps repeating itself over and over and over again. What do we use? Sine or cosine, right? Something that's periodic, because it's going to just keep swinging back and forth. So we've got a pendulum swings with a position function given by t equals 20 cosine pi over 2 t. T is in seconds, S in inches. So what this looks like is you've got this pendulum that is swinging back and forth on a little rope, so it can come out to here, come out to there. And we've got a little scale on the bottom here that's measuring how back and forth it's going. And the way this equation is set up, because the amplitude is 20, it should go out to 20, it'll go out to negative 20. So this is like our little position scale down there. And that pendulum is just swinging back and forth and back and forth and back and forth and doesn't stop. Okay, and then this is the equation that models it. Not making you come up with that one this time, we're just giving it to you. First question for you. What is the pendulum's maximum speed? And then not only that, when does it occur? Okay, so we need to know velocity then, right? So the velocity equation of this thing is, see, the derivative of 20 cosine pi over 2t. Derivative of cosine is negative sine, so it would be negative 20 sine pi over 2t. And then because of the chain rule, I got to multiply by what? Here's the inside substituted little piece. What do I got to multiply by?
Pi over 2.
Pi over 2. So my velocity is negative 10 pi sine pi over 2t. Maximize that, or minimize it, because the speed is the absolute value of that, so the max or the min would be good. Maximize velocity, I have to do the velocity's derivative, right? So I got to get acceleration then. So one more time, another derivative. So derivative of sine is cosine, so it's negative 10 pi cosine of pi 2t. But I got to multiply again by pi over 2. So this acceleration equation is going to be negative 5 pi squared cosine pi over 2t. And when this is equal to 0. Because that'll help me figure out where this thing has its maximum speed. So if I set this equal to 0, to see how this negative 5 pi squared, I can just divide it away and it doesn't really matter. If it's equal to 0, right, divide the whole thing by that, divide 0 by that, it's gone. So cosine pi over 2t equal to 0 would be where its maximum speed is going to happen. So this equal to 0, so I got to do an inverse cosine of 0 equals pi over 2t. Okay, so when is the cosine equal to 0? Think of your unit circle.
Pi over 2, 3 pi over 2.
Pi over 2, 3 pi over 2. Okay. And then et cetera, right, from there. So if I solve this one, t is equal to 1. If I solve this one, t is equal to 3. Okay, and do you see how there's going to be more and more and more and more and more answers? Because it's going to keep coming back, okay? So every odd integer is going to be a solution then for this one. Yeah?
Is inverse cosine not limited to the top?
It is limited to the top. In this case, I guess maybe saying that as an inverse cosine was a little bit misleading, because the solution to this would be, like, the inverse cosine gives you one solution, but then this thing technically has a whole bunch because it just keeps moving. So maybe writing it that way wasn't the best choice for me to do, but yeah, it would technically keep repeating. So t equals 1, 3, 7, etc. seconds. Would be when it occurs. Okay, so that answers this question. And then we also want to know, what is the max speed? So what do I do with the 1, 3, 5, 7, etc.? Plugging it into what? The velocity, right? Okay, so let's try one of them. They should all give me the same thing. Positive or negative, doesn't matter because it's speed, right? So I could take any one of those numbers, plug it in here. Let's try the 1. So v of 1, negative 10 pi sine of pi over 2. So that would get me, sine of pi over 2 is 1. So it's negative 10 pi. But remember what I said, we're talking speed, right? And speed is the absolute value of velocity. So what is the actual speed of this thing? Just 10 pi, okay? Ten pi what? What should be the units for this thing? Flip that around. There you go. So,
How do you know if that's not the minimum speed? Like, those times that they're...
what I did was I made the velocity equation, not the speed equation. And by taking the derivative equal to 0 of that, I'm maximizing and or minimizing the velocity, not the speed. And a minimum velocity is just going to be the opposite of the max. And so I knew that whether I got a min or a max of the velocity, it's actually the maximum speed. Yeah. So then I wasn't in trouble. So, yeah, so 10 pi inches per second would be answering the question, what is the actual max speed? Okay. And that should have each one of these intervals in the time. Okay. I was going to ask you some acceleration questions, but we're out of time, so we'll stop there. Everything should be up on course sites for you. Tomorrow's your online day, so have at it, and we'll see you on Monday then, unless you want to stop in tomorrow.